Welcome. This is Dr. Gary Sullivan, Chief of R&D and creator of IOP Technology. This video both summarizes and expands on a peer-reviewed article published by the American Chemical Society and authored by myself and Shannon Nelson, our firm's CEO. The article shows how two apparently dissimilar areas, engineering and sociology, can be combined to predict actions, attitudes, and postures that affect gender diversity. The integration begins with an obvious insight. Most of us go to work to the same place every day, we drive the same car to get there, and come home to the same family every night. This kind of environmental regularity allows us to develop and reuse strategies that cope with our particular stable conditions. These strategies are patterns that cause us to pay attention to particular things, to interpret them in a specific way, and to respond to them in a predictable manner. If our strategy produces an acceptable outcome, it is a good strategy. Strategies can differ, but no strategy is any better or worse than any other. But what is perfectly functional on an individual basis can be dysfunctional in a group. For example, a person may live in an environment that favors input specificity. Paying attention to detail. People using this strategy might be put off by another person whose different life context causes them to focus on generalities rather than specifics. Similarly, someone whose personal environment favors an action output might find another's interest in time-consuming planning to be annoying. And linking different input and output options requires a different reasoning. And reasoning that makes sense to one party can be seen as flawed by the other. This is why reconciling divergent positions can be difficult. But it is this reasoning box that also gives us flexibility. We can and do adjust our favorite strategies. The thing that triggers those adjustments is context. For example, our reasoning may relax a rigid input standard for decisions with an inconsequential impact. Or a preference for complete planning may be softened if the context signals that a major gain is available from a prompt response. The process box can also be affected by structural context. Structures are conventions, arrangements, norms, and other features imposed upon a situation without being an inherent part of them. For example, a profession might adopt standards to ensure efficiency and effectiveness. A person who favors speed of response more than certainty might be restrained by a standard that requires documentation. Documentation takes time. Restraint is built in. Engineering's process box is what adjusts the psychological preferences of the individual to better match the conditions that are being confronted. But for engineering's process box to be useful in predicting and guiding behavior, we need some way of signaling context. Sociology can provide that way. Its focus is on the patterns of interrelationships. Things like roles, rules, social conventions, norms, and organizational structures are sociological at their core. What is missing is a way of getting the sociological signal to engineering's classical model. We need a tool, and that tool is IOP technology. It has a fully developed theoretical base, what causes what and why. The theory is built on the classical engineering model, and it is completely understandable. No smoke, mirrors, or obfuscations. The theory has been validated across all 8. Yes, there are 8 accepted validity standards. Its reliability has been proven using standard test and retest protocols over periods as long as 18 years. Its results are stable over time. And it's used for over 25 years by major corporations, nonprofits, and universities testifies to its operational validity. IOP works in practice as well as on paper. And the characteristic that makes IOP uniquely applicable to groups is racial measurement. IOPT is not confined to merely grouping things into categories like introvert and extrovert, or simply sorting them into rank orders like big, bigger, or biggest. It measures things exactly. This means you can use arithmetic to add, subtract, multiply, and divide, something lesser levels of measurement cannot do. This makes IOPT a natural bridge between engineering and sociology. Because IOPT can accurately predict behavior on an individual and group level, it can accurately gauge the likely impact of various contextual variables. Our American Chemical Association article applies this sociometric tool to a real problem in chemical sciences and chemical engineering. Women account for 34% of the chemistry workforce, and only about 17% in chemical engineering. Why? The required intellectual capacities in both fields is about the same. The educational demands are similar. The nature of the work is roughly comparable. And chemical science pays 31% less than does chemical engineering. So, why do twice as many women ignore their economic interest and choose chemical science over chemical engineering? Well, we can start trying to find out by looking at the men. There is no statistically significant difference in the profiles of male scientists and male engineers. So, whatever is causing women to avoid engineering does not apply to men. A good place to start looking for this gender-sensitive trigger is in the culture of the two fields. And what we are looking for is something that is different between these two fields. Now, culture is just a system of beliefs which have been rank ordered. The rank order of beliefs is what we call values, and the rank order position is what we use to select our behaviors in real life. For example, we might believe that certainty of outcome is important to a decision. We might also believe that speed of response is important. Change the rank order of these two beliefs, and observers will infer a very different personality. The image of a cautious thinker could be replaced by that of a responsive adventurer. So, we are looking for differences in both the beliefs and their rank order. Our study of the engineering personality described how engineering activity generates consistent behavior that can evolve into cultural beliefs. Our engineering insight study found that engineers at all hierarchical levels tended to share the same profile. This commonality of thought creates a stronger culture than is typical of other professions. Our Women in Engineering study identified the consequences of failure as a cultural driver. Failure in science is expected. It's the nature of experimentation. Failure in engineering gets you fired or sued. The norms, procedures, and practices developed under this constraint has produced an unprecedented stream of advances. But it has also unintentionally disadvantaged women. Our engineering education study showed how the beliefs created by these structural conditions became embedded in the intellectual fabric of the profession. These cultural beliefs were set in stone at a time when only the male chemistry, biology, and circumstance had to be considered. They are practiced today because that's the way it's always been, to the continuing disadvantage of women. And our study on the root cause of gender bias in engineering identified a masking effect that hides the source of bias from everyone, men, women, scholars, and practitioners. And that mask involves false equivalencies. The dominant strategies for both science and engineering are the same. They both favor some kind of predefined input scheme, formulas, theories, well-specified hypotheses, that kind of thing. And both target thought-based output. Things like plans, judgments, assessments, strategies, preparatory type of actions. The identity of both input and output elections in the dominant profile of both genders creates the false equivalency. What is hidden is the difference in secondary styles, the approach people use when a favored strategy is not applicable. Women fall back to things they know will work, maybe not optimal, but adequate. Men share this secondary strategy, but at a much less intense level. And their secondary idea-oriented RI style is appreciably higher than that of women. So, the highly visible primary styles are the same, and the less frequently encountered secondary styles are different enough to be noticeable and statistically significant. So what? Well, remember the pronounced effect we got by just flipping the ordering of two beliefs? That's what's happening here. When they are displayed, the difference in behaviors of men and women can generate tensions. These tensions can then become the basis of a cultural belief. And because the problem is rooted in the secondary styles, it only appears intermittently. For example, a cultural belief that women lack creativity might be periodically reinforced. This and similar derivative behaviors can then feed into a cultural matrix feeding a bias. And B.F. Skinner, a notable psychologist working in the 1950s, showed that intermittent reinforcement is the most durable of convictions. Once a belief is installed, it tends to persist over time. A strong LP style is a rational choice for women. Its focus on proven input limits the challenges to the viability of a choice. The action output limits the need to defend that choice. This combination effectively shields women chemical engineers from hostile elements of the culture. So, chemical engineering culture appears designed to attract the kind of women who perpetuate the culture that tends to act against their interests. How's that for a catch-22 situation? However, it's not all gloom and doom. Our research into women in engineering leadership showed that those women whose profile matched the general leadership profile within chemical engineering were being promoted. In other words, engineering does not impede women who got in and stayed in spite of the culture. The problem is that the culture discourages these right kind of women from ever entering in the first place, thus limiting the pool from which leaders can be drawn. People who decide to duplicate our analysis have to be careful with their samples. The bias condition does not apply everywhere in chemical engineering. In process engineering, women make up about 34% of our sample, exactly the same number as women in chemical science. And men and women process engineers share essentially the same information processing profile. So it appears that something in the structure of process engineering is washing out the bias effect thoroughly enough to double the women's participation rate so that it equals that of chemical science. And that structural something is the unique nature of the work. Process engineering involves controlling continuous processes involved in converting raw materials into value-added components. Process engineers work with large volumes, exacting requirements, complicated mechanisms that have to work 24/7, and which carry serious consequences for failure. Satisfying these structural conditions effectively creates a level playing field. Competence is easily demonstrated and is visible to all. The existence of this area of gender equality is sending a clear signal that the same results are obtainable in other areas of chemical engineering. If that condition were to happen, the raw brainpower of the field would be substantially enhanced. And the perspective of half of the world's human population would be better represented. Our earlier research studies offer many ideas, avenues, and techniques for improving the conditions for women. And our research blogs provide detail on the data, methods, and references used in these studies. In final analysis, they all boil down to creating an environment that recognizes and leverages gender-based differences. Everybody wins, man, woman, and the organization. Thank you for viewing this video. If you would like to learn more about IOP, please visit our websites at iop.com or oeinstitute.org. Both sites have much more information on where IOP has or can be applied. Thank you again for your interest in IOP technology.